So a couple of other things I wanted to mention. We looked at the grade calculator. That might be more beneficial towards the end of the semester, especially when you know, like, for instance, going into the final, like, what do I need? I get a lot of emails. What do I need to make on the final to get a B or whatever? That's one of the reasons this is there. You know all of your averages here from the grade book. And by the way, I don't use MyMathLab's grade book, so if you're going off of that, it's not accurate. It doesn't include things that you didn't do. So, if you did 2 assignments, one's 100, one's a 0, it'll say your average is 100 when it's really a 50. So I use the D2L grade book for all of our class grades. So you know where you're standing after the 3rd exam, then maybe you want to make a B in this class. What's the minimum I can do on the final to make a B in this class? So 48 on the final, that's what you need to make a B. What do I need to make an A? You can do that as well. Okay, so hopefully that's helpful at some point in the semester. All of the recordings will be posted here. I'll try to keep this up top. As I make more announcements, these 2 things will get pushed down. But these 2 will always be up. Okay. So I would just recommend following this link and then probably just bookmarking it, just in case. They do have a tendency to get buried. I'll try not to let that happen though. So those will be all uploaded to this here. If you miss a class, you can watch these, get caught up. The other thing I wanted to mention was that our class notes, once we complete them in class, will be uploaded here in the completed notes section, but the blank notes are here for you to print out before the class. Okay, I would recommend doing that. It'll save a lot of writing. I have the first 2 sections already printed out, so everything outside of section 6.2 would be your responsibility to print off if you wanted to utilize those in class. Okay, so you'll just be working the same stuff that we're working on the board, and then once I complete the notes, I'll upload them here. And again, if you missed class, you can have access to the notes as well. And hopefully that helps. Yeah.
Are we going to be doing most of our note-taking off the print-offs?
Yeah.
Okay.
Yeah, all of our notes will come from these. Sometimes we don't have time to get to all of the examples in the guided notes, so just keep that in mind. They're really meant more as like to help you out, not write so much, and maybe focus your attention a little bit better. But not everything we put in there we'll have a chance to cover. We'll cover the main ideas and topics and examples and stuff, but some of them might be similar and we'll skip them if we need to. So there. The exam reviews I'll post here. I'll post exam keys and blank exams after the exams have been handed out, or graded rather. And then that way you can print off the blank exam, and maybe that's a good way to prepare for the final, just to kind of test your knowledge and see, oh, like looking at the key, I missed this one and this one. I need to look over integration by parts again or whatever. So that's pretty much it. Go ahead and hand these out to you. 6.2, how many took Calc 1 here? Just by show of hands. Okay. So 6.2 was actually covered in Calc 1, but we will look at it again. That is probably a good candidate to where we won't do every example in the notes, but we will revisit that. So you've seen it before if you've taken Calc 1 here. You might have seen it if you took Calc somewhere else too. Anybody have any extras?
We have an extra. And then he's out
So this, starting out, chapter 6 really deals with what can integration do, or what can we do with integration. If you remember from Calc 1, what could we do with integration besides just finding a straight antiderivative of a function? What else did we use integration for?
Related rates.
Do what?
Related rates.
Related rates were derivatives? Yeah. What else?
finding the space under a curve.
The area under the curve, particularly the net area, right? The sum of the positive and negative contributions. And that's pretty much it, right? That's all we really looked at in Calc 1 in terms of what can we do with integration. So chapter 6 gives us some more insight into what we can do with integration. And then the next chapter, these chapters are new, so I have a tendency to refer to them as the old chapters, but they're not. So chapter 8 deals with more techniques to integrate, because right now the only technique we have to integrate, legitimate technique, is U substitution, right? Chapter 8 we look at other techniques to help us integrate sort of, more varying types of functions, products, quotients, stuff like that. Okay, so just as a reminder, that when you use a U substitution, what derivative rule does that undo? The chain rule. So if we have a chain rule type of situation in front of the integral, then a U substitution is what's undoing that for us to allow us to find the antiderivative. Okay, so we look at velocity and net change in this section, then we'll look at areas between regions, then we look at general slicing method, which leads us into volumes. So you can actually compute volumes, a three-dimensional thing, using a two-dimensional approach. Then we look at some physical applications like work and force. We look at some hyperbolic trig functions and stuff like that. So that's really chapter 6 in a nutshell. Like, what else can we do with this operation? Okay, so some of these first few examples may be gentle introduction, but suppose we drove at a constant 50 miles per hour throughout a 4-hour trip. What's the total distance traveled, and what does the graph look like? Okay, so these are pretty straightforward, but we're going to kind of piece this together. 50 miles per hour for 4 hours. So this is here. What's the total distance traveled? Yeah, 200 miles. Distance, 200 miles. But just the one thing we want to take note of here is it's a pretty simple function, but what happens when we compute this area under that, and rather between the function and the t-axis? What is the area of that? The area is also 200, right? So this area is also 200. Okay. Hopefully, what does the graph look like? We graph that. So hopefully that's pretty straightforward. Similar thing, a little bit more different situation though. We travel 30 miles per hour for 2 hours, then 40 miles an hour for a half hour, then 20 miles an hour for 4 hours. Again, what's the total distance traveled? So we're going to make the same connection here. And really with these two examples, we'll note below, but both of these have graphs that are strictly above the t-axis or the x-axis or whatever. So we'll make a connection there. So 30 miles per hour for the first 2 hours. Then 40 miles an hour for the next half hour. And then 20 miles an hour for the next 4 hours. That's a little off, but I think that's fine. For the next 4 hours. So there's one. Where would we end up at? We have 2.5, 6.5. There. Well, let's say there. Close enough. So total distance traveled would be what? Distance traveled is what? 160 miles. And again, we see if we compute the area of this rectangle plus this rectangle plus this rectangle, that area is also 160. So, the idea is that when we're dealing with a speed, or more generally, a rate of change is positive, and time is on the axis, the vertical axis, or rather horizontal, then the blank under the curve is the accumulated distance, or what? So what are those other two blanks? Area. So the area under the curve is the accumulated what? All right, yeah, good. You're on the right track. Displacement. In general, though, displacement is what? Like, what is displacement? It's a change. It's just a change in a particular thing. It's a change in position. Okay. So the area under the curve is the accumulated distance, or more generally, it's the net change. Net change is more broad. Really, it's change because everything's positive. We don't have positive and negative contributions that give us that net, right? Like your net, you have your income, but your net income is minus things that you give away. Okay, so that's hopefully pretty straightforward, gentle introduction into kind of where we're going with this. So if you want to talk together and try to complete these next 3 examples, just note that there will be multiple answers, so your answers could and probably will vary. Just try to think of a realistic situation. Don't get all like sci-fi. Okay, so just take a few minutes, let's say 5 minutes, and feel free to talk together or whatever, and come up with some graphs.
That's what it is. One doesn't want to stop. Realistically. That's true.
Yeah.
Drop down.
Yeah.
Eventually, the guy is going out. Let's see, the end of the was from the leak, which caused whoever was in it.
Yeah, exactly.
And they started losing blood, which made them rush to the hospital.
Can take maybe another minute.
The next one, what is the rate of decomposition?
Okay. So does anyone feel bold enough to come draw what they got? Anybody? If not, you can just kind of describe it to me. It's just hard when people go, oh, it should look like that, you know. So we have a rowboat springing a link. RT is the rate of water flow into the boat. Cool, thank you. All right, what do y'all think?
Good job.
Thanks for your bravery, appreciate it. Yeah, certainly reasonable, right? We would expect water to start seeping in and possibly continue seeping in. Maybe something different that you obtained might be more realistic. You know, the boat has a finite capacity, so water could start flowing in and then eventually would fill up the boat, right? So it kind of flatten off. You know, either way, totally fine. Maybe you got something different. Okay, so there's the graph. What does the area under the curve represent?
The amount of water in the boat.
The amount of water in the boat? What do y'all think?
Yes.
The area under the curve represent the amount of water in the boat. Does it seem reasonable? Okay. So just as a reminder, when you compute the area under a curve, what are we doing with the units? Let's back up. What happens when we take a derivative? What do we do with the units? What is a derivative?
The unit is, it's a rate of change, so if we're taking the antiderivative or integral, we're going up a unit, we're multiplying by the units on the x-axis.
Right. So backing up, when we take a derivative, remember the derivative is just a slope. It's a y unit over an x unit. But when we compute, remember this notation, when we compute the antiderivative, remember this function essentially gave us the height of a rectangle, and then we multiplied it by the width of the rectangle. So when we compute the area under the curve, we take the units on the vertical times the units on the horizontal. So there's no units specified, but it doesn't really matter how we're measuring that water. So let's just, for argument's sake, let's say the rate is measured in gallons per minute and time is measured in minutes. When I multiply that together, the minutes cancel out minutes, cancel out, and all I'm left with is gallons, or liters, or quarts, or whatever. So the amount of water in the boat. So I think that's just as important to realize what we're doing with units when we take an antiderivative or an integral. But yeah, any questions on that example? All right. Patient is losing blood at a specific rate. Anyone want to draw that? Anyone want to illustrate with their fingers? Okay. Again, situations could vary depending on what's happening here. Oh, let me change this for you, sorry. Let's do that, yeah.
Oh yeah, you're red, like the blood losing.
Appropriate. Okay, thank you. What do y'all think? Okay. Seem reasonable? If this were a rate, you know, here would be 0. Would we expect them immediately to start losing, you know, 10 milliliters of blood per minute? Could be, depending on what's happening, right? And did anybody come out with a different scenario? All right, I suppose that's good enough. I've had other people say, well, they would start to lose blood, and then lose a lot of blood, and then eventually all of their blood would be out of their body, right? So, again, totally accurate, but depends on the situation. What does the area under the curve represent?
Total blood loss.
The amount of blood lost, right? So again, think about the rate they're losing blood. I don't know, anybody familiar with health stuff? What is blood usually measured in? Pints? Okay, well, how do you abbreviate pints? Is it PT? Whatever.
Sure, it is now.
Pints per minute, this is minutes. Again, if we find this area under the curve, then what we're taking are the T units, multiplying them by the RT units. Okay, so the amount of blood lost. All right. How about the IV? Anybody want to draw that? Or show me what you got?
Wouldn't it just be a horizontal line?
Okay. Like that? What do y'all think? Okay, so that just means you're getting an IV at a constant rate, probably the most accurate representation of how IVs are administered. And the area under the curve represents, yeah, the amount of medication into the patient. Okay. All right, again, that's sort of a, you know, just kind of an intro to this stuff. Do y'all have any questions at this point? We haven't done anything with integration yet, so. All right, some of us may have forgotten, so we're going to go ahead and remind ourselves. When we talk about a position function, generally for us, it's described as S of t. You know, if you're in physics, it's probably different. But say we have a position function given by S of t, then how do you compute or find the velocity function? The derivative. Okay, so the velocity v of t is the derivative of the position function. The rate of change of position with respect to time is the velocity, and acceleration was the derivative of velocity. So a of t is the derivative of velocity, or the second derivative of position. What's the derivative of acceleration? Derivative of that? Okay, so y'all know where this is going. Snap, crackle, pop. That's funny. All right, so if you forgot, there's a reminder. And by the way, you should be familiar with basic antiderivatives, like what's the antiderivative of sine, what's the antiderivative of 1 over the square root of 1 minus x squared, 1 over 1 plus x squared. Those things you should still remember, and if you haven't, they're really easy to review. So that's kind of the assumption, is that we're all familiar with the process of how to find an antiderivative, and use the fundamental theorem of calculus, which a few examples we'll go through just as a reminder, but some of them we're going to end up shortcutting just for time. All right, so I'm going to draw this position function, maybe describing trip from my house to school, and I'll try to do this. One of these days I'll just put this in with a computer. So that's straight. Pretend that's straight. All right, so that's my position function. What would the velocity function look like? Again, velocity being the derivative of the position function.
It would increase linearly and then drop to 0 and go negative.
Right. So yeah, what's for sure, maybe not for sure, but I think the easiest portion is kind of here. What's the velocity doing here in between these two lines?
0.
It's 0, right? It's well, the position remains as a constant, but if your position is constant, that means you're not moving, right? If time is ticking and I'm standing here, my position is, here. Velocity is 0. Remember, the velocity is the rate of change. If I looked at the slope of the line here, the slope of the line is 0. That's my velocity. So velocity is 0 here. But notice here it starts out at 0, and then it gradually increases. So we're gradually increasing. Just imagine what your pencil looks like on that graph. And then it decreases until it's flat or 0. So it increases, and then it decreases to 0. Then it's 0 for a while. Then after this point, the velocity is decreasing, and then it starts to increase a little bit before it, flattens out. That's supposed to be kind of flat here. So, something like that. So the things we want to look at here are specifically displacement and distance traveled, and then we'll sort of transition that into a more generic thing where we look at a net change. But let's see if I have room here. As far as the displacement goes, what is the displacement across this time? Zero? I thought I heard somebody say that. Right. What do y'all think? Displacement 0?
Yes.
Total change in position. I start here and I end here. So, this is my trip to school. I get on the interstate, I park, I stay here for a while, and then I go home in the same but opposite direction. So if I say, well, what's my displacement from my house to my house? 0, right? But we see that illustrated here with this graph of the velocity function. And how is that connected? Displacement is what? The net area, right? So we have this area above the axis, whatever that is, and this area below. Again, it's not that we're saying negative area. We're saying that it's negative because it's below the independent axis. So the displacement is 0, but this is also the same thing as the net area on the velocity function. Okay. So how would we then compute the distance traveled?
plus
A plus A, right? Because the distance here is, whatever, it's like 20-something miles. Let's just say it's 20 miles from here to my house. But I'm also traveling 20 miles back to my house. So that's a total of 40 miles as far as distance traveled versus displacement. Does that make sense? I know a lot of you are already in physics too, probably, but some people do take this class as a standalone and might never have had a physics class. So when we look at the distance traveled, what we have to do is we have to take, and when we're specifically looking at the velocity function, again, we have to take the area above the axis, and we have to add to that not the area below the x-axis or the t-axis, right? But we have to make this negative as well. I know I wrote that plus in there, but just if you wanted to view it as a minus the negative a, same thing, right? But really we're just multiplying this by -1 so we can make this positive and add those two together in the sense of an area. So you can think of distance traveled as just the area, right? If this is your, maybe this is your property and this is a river, right? The area is this property, this acreage and this acreage. You wouldn't say I have 0 acreage. That's the same thing as area. Net area is when we take the signs into consideration as well. Okay, so does that make sense? Easy enough to follow? So then we're going to put that in the context of our math and say that the displacement or the net change from a time to another time, t1 to t2, is just the integral from t1 to t2 on the velocity function. The how do we denote that? Net area. Okay. The distance traveled, we have to look at the integral from t1 to t2 of the absolute value of the velocity. And again, what does the absolute value do for us?
makes negative positive.
It just makes negative things positive, just like we did here. We made this negative thing positive just by multiplying by -1. So that's the absolute value is doing for us. And so when we look at that, gives us total distance traveled. Here, as a sort of a general thing, when we look at a function and we say, well, what is the absolute value of that function? If you remember from the definition of the absolute value, it's what the absolute value of whatever is in here. It's defined as that thing as long as that thing is 0 or positive. But when that thing's negative, the absolute value simply multiplies it by -1, because that's what turns it into a positive. So it's the negative of f of x when f of x is less than 0. Right, so do y'all remember the absolute value functions? Usually you see the absolute value of x right here. Okay? So again, that's just reinforcing what we already did above, where we had the negative area. We had to attach a negative in front of it to compute this. And so we can calculate the displacement all day. If we're given a function, you don't even need to look at the graph. You just throw that in the integral. Fundamental theorem of calculus, there's your answer. The distance traveled, it does involve a graph, because before we throw this negative in front of something, we've got to be sure that the function is below the axis. Functions or pieces of the function that are below the axis are the ones that get multiplied by -1. So if and when you're ever asked to compute an integral like the distance traveled, you will either be asked to graph that first, or a graph will be provided. Otherwise, you can't do it. Okay, so do y'all have any questions about either one of those? Feeling all right? If this is all elementary, don't worry, the class accelerates rapidly. All right, so we'll take a look at this velocity function on the time interval from -3 to 2. And we're going to do a couple of things. We're going to graph the velocity function over the interval and determine where the motion is in the positive direction and when it's negative. Then we'll find the displacement on the interval and the distance traveled. So, oops, why is that being weird? So let's graph the velocity function. It's a polynomial. We're going to take velocity, and we're just going to factor that out. So pull out the greatest common factor. It's a quadratic, pretty straightforward. There's our factored version, which then gives us the fact that we have our zeros at 1, -2, and 0. Let's say -2 is here. 1 is there. Okay. All right, so those are our zeros. Let me make those more pronounced. And then what else is this thing doing? I mean, yeah, we could throw that into a grapher, but you don't have a grapher on the exam.
It's negative before -2.
Okay, so just so maybe a crash course in how we graph these things. We plot their zeros or their x-intercepts, and we look at the function's end behavior based off of the leading term. Remember, end behavior and limit at infinity is the same thing. So as this function goes off to infinity, if we're drawing a complete graph, it's ending up here and it's starting down here. What do we do at each zero? There's only two things you can ever do at a zero. Either the function's going to cross through it or it's going to bounce off of it. So how do we know if it crosses or bounces? Yeah, multiplicity. Who said that? Multiplicity. Meaning, how many times does that zero occur? If the zero occurs an odd number of times, you cross through. The higher the odd number, the more flat it crosses through. Multiplicity is even, then you're going to bounce off. The higher the even multiplicity, the more flat it bounces off. Do y'all remember that? College algebra, pre-calc stuff? All right, now you do. So, but we're not starting with these arrows, right? Because we're on a closed interval. So we're not continuing off to infinity. We're going to stop here at +2, and we're going to begin at -3. So there's our domain. We're graphing it there. Starts down here, gets to this 0, crosses through. We have to cross through this 0, so at some point it has to bend down, cross through this 0. It has to cross through this 0 to end somewhere up here. Let me redo that, but that's the graph. I mean, that's really all we need from the graph. We don't need to know the local mins and the local maxes or anything like that. I'm going to scoot 2 over because I just didn't give myself enough space. I'm just going to stop it there and say that's 2. All right. So hopefully that was just a crash course in how you graph polynomials. Might not have been the best, but we'll just say -3 is there. All right, so there is the velocity function, v of t. Okay, now we've got the graph, so how do we determine when the motion is positive? In the positive direction, rather. Positive y values, positive velocities. And that's generally just how it's set up by convention. Just like generally a negative velocity or acceleration is going down, a positive is going up. Just conventionally, that's how it's set up. If it's set up some other way, it'll say, but it's for us, it's not. Okay, so let's write this here. We've got motion in the positive direction. Let's see if I can fit it here. Motion in the positive direction is when V of t is positive. Okay, so we're just describing now the intervals in which the velocity is positive. And so what are they? -2 to 0. So t is in here. It's an interval. Are we including -2 in that? Yes? What do y'all think? No?
Is it positive or negative?
Say that again?
No, because 0 isn't positive or negative.
Right. So, in fact, we would not include the endpoint because we know that the velocity is 0. It's neutral. It's neither positive nor negative at -2. Same thing with 0. We're not going to include that because we know at 0, the velocity is 0. Okay. So in between -2 and 0, and where else? From 1 to 2. Are we including 1? No, 0 there. We're including 2?
Yes.
Yes. Velocity is positive still at 2. Okay. Very similar thing for when the motion is negative, in the negative direction rather. Motion in the negative direction when velocity is negative. Okay. So velocity negative from -3 to -2. Again, we're not including the -2. Do we include the -3? Yeah, velocity is definitely negative there. Okay. And negative from 0 to 1. Since both of those are zeros, we don't include either one of those. And, specify what does it mean for the velocity, or rather for the motion to be in a positive direction. This is really just depending on how you choose to set that up. But I think typically motion to the right, if it's a one-dimensional motion to the right would be positive, just because that's where the positive values are. But again, that could change. For us, generally doesn't. But all right, questions on any of that? All right. So now then we've got the graph. We can find the displacement over the interval from -3 to 2. And if you remember from the previous page, the displacement is simply the net area. So we're just going to integrate from -3 to 2 our velocity function. So once we compute that integral, then we have the displacement of that object from -3 to 2. So just a quick refresh. Here we've got the sum and difference of terms. We can look at the antiderivative of each term individually. So remember, the antiderivative, basically you can distribute it across sums and differences, right? And then all of these are just powers, so we're just using the power rule. So do we all remember the power rule? Hopefully, if not, you gotta look it over, or we'll do it here. So what do we do to find the antiderivative of t cubed? Divide, yeah. Add 1 to the exponent and divide by the same result. So it's t to the 4th over 4. Antiderivative of t squared. Again, add 1 to the exponent and divide by the result. So t cubed over 3 minus antiderivative of 2t is going to give us t squared. So we add 1 to the exponent, gives us t squared over 2. The 2 and negative 2 divide out. And remember, once you find the antiderivative, all you have to do now is plug the endpoints in. I hope this is familiar. In what order do we plug those in, and how do we plug those in? Upper minus lower. So we're going to take a t-value of 2, plug it into our antiderivative. So I'm just going to write it like this, just so we can see. All right, so there's the antiderivative evaluated at the upper limit. 2. And then you have to subtract off the antiderivative evaluated at the lower limit of integration. So we have negative 3 to the 4th over 4 plus negative 3 cubed over 3 minus negative 3 squared. And then so once we compute what that number is, that's our displacement. Okay. Coming back to you. All right, so type in your calculator, and we get that to be 5/12. Just if you're rusty on antiderivatives, and our textbook, Chapter 4, Section 9, there's a table of, I believe there's still a table of all of the antiderivatives. So you might want to look over those. You know, sine, cosine, not tangent, secant squared, stuff like that. E to the x, logarithms, things like that. Okay. Questions on the displacement? Okay, distance traveled, that's the one where we have to look at the absolute value of the function. So now we're going to default back to the graph and say anything that's below the t-axis, we have to put a negative in front of it. So really all it equates to is subtracting that quantity off, because that quantity is already negative. And when we subtract off the negative, it makes it a positive. Okay, so the distance traveled over the interval, I'm going to write it out. I put a line here. Just as a reminder, it is we're computing the integral from -3 to 2 on the absolute value of our function. What was it, minus 2t? dt. Bringing that down. So the areas that are above the x-axis, or sorry, the t-axis, this area here and this area here, that's fine. We just leave them alone because they're positive. So that's the integral from, let me label these, this was -2, that was 0, and this was 1. So that first area here above the axis we go from -2 to 0 on that function, t cubed plus t squared minus 2t. Same thing with the other area. We're just going to add to that the integral from 1 to 2 on our velocity function, t cubed plus t squared minus 2t. I'm going to run out of space to write it in a line, but now that we've addressed those positive areas, like we said, you never do anything with them. You just leave them as is. Is everybody okay with that? The negative ones, we just make negative. So this area here, negative, and this area here is negative. Okay, so we're going to go from -3 to -2 on the velocity function. And again, we're not worrying about, at this point, the absolute value, because the positive things are still positive, and this thing is negative, so we're just going to subtract that off. That's it. There's your negative f of x right there. No absolute values are involved when we do it this way. And then subtracting off the other negative area from 0 to 1 on the velocity function once again. Okay. So that's tedious. It's not that it's hard to do, but expect some of these in your homework. It does take time to figure these things out. Okay. Does anyone have any questions on how we've arrived here? So we already computed the antiderivative. It's just we'll have different values to plug in. Okay. So are y'all confident with being able to do that? If you're not, send me an email, and it's totally fine. It might have been a while since Calc 1 for you. It's totally understandable if you forgot how to do this. But again, we're hitting the door running here, so you've got to get back up on this. So email me if you have any issues or whatever. I'll be happy to, work with you or whatever. But you should verify this for yourself, that when you compute the distance traveled, we come up with 133 over 12. And whatever, if we can say that's about 11.0. We forgot, 11.08. We forgot our units here, so we should put our units. I forgot. So velocity, meters per second. So displacement and distance traveled in meters. So 133 over 12 meters for distance, and 5/12, whatever this is, meters. Okay. All right. So hopefully nothing terribly new with displacement. And now that we've seen how to handle an absolute value in the integrand, hopefully that's not scary or mystical either. Does anyone have any questions? All right. So future value, we're going to look at that as well. One of these methods you have done before. You might remember those initial value problems in Calc 1. If you're in physics, you've done those. But in Calc 1, it was sort of like a brief introduction into differential equations. So we're going to look at both methods. Method 1 is called, well, I guess method 1 we're just using an antiderivative. All right, so what we know is the initial position, S of 0, and we want to find the future value. We want to find S of t for any time greater than or equal to the initial. Okay, so what are we going to start with? If we know the velocity and the initial position, how do I get back the position function from that? So position is,
Position original
okay,
plus or minus.
It's the antiderivative of velocity.
yeah, right. We're doing the antiderivative method. So the position is the antiderivative of velocity. But we know that when we actually take the antiderivative of a function, that we really get that more or less this is s of t plus some constant of integration, right? So it's really not s of t. Somewhat misleading. But we do know the antiderivative of velocity gives us s of t plus c. And we know the initial position. So what do we do from here? We plug in what?
0.
Yeah, we plug in this initial condition to find c. So here, once we have this function, then we use the initial condition to find c. And c isn't always the value of the position initially. It just really depends on the function. Okay, so there's the antiderivative method. Second method, method 2, we're going to call this fundamental theorem of calculus. Fundamental theorem. Fundamental theorem of calculus to do this. And they're both, it's both the same, right? It's just two different ways of doing the same thing. All right, so we're going to start out with the antiderivative, again, of the velocity function. Here we're just going to use the dummy variable x because we're going to go from the initial to some unknown time. So from 0 to t on v of x dx or v of w dw, whatever. It's just, we don't want these variables matching here. Okay. However, we know that from this, we can say that's the same thing as the integral from 0 to t. The velocity is the same thing as the, let's go with this. The velocity is, sorry, I messed up, the derivative of position. Okay, so looking at it that way, what will that be? What happens there? Maybe not necessarily with the bounds at this point, but what happens with the integral of s prime? It's what? Yeah, it's just s, right? If I take the antiderivative of this derivative, don't they undo each other? So the antiderivative of s prime is s. We found the antiderivative, so all we need to do is evaluate this. And again, this is a x value. So this is, we're evaluating x equals from x equals 0 to x equals to t on s of x. And what that would give us, s of, we plug in the upper limit, s of t, and then we subtract off the lower limit, right? So s of t minus s of, s of t minus s of 0. Let's see if I can fit this here. So that's what all of that stuff evaluates to, and how does that help us? Well, it helps us because, again, what we're after is this s of t function. I can find the constant of integration via the initial condition. But notice that initial condition is now here. S of 0 is my initial condition. S of t is what I want to find. So let's look at what we started with and what we ended with And we're going to take those two statements and just solve for S of t. So what we end up with is that S of t is the initial position plus the integral from 0 to t v of x dx. And when I find this integral from 0 to t of v of x dx rather, what is that actually computing for me? Well, close. Not the distance, but the displacement from 0 to t. So we have the displacement, the change in position from 0 to t, plus the initial position gives us the final position, right? So that's what we're dealing with in that particular statement. I think that's below. No, maybe not. I'll just go ahead and that's what we're operating with. I'm going to take from the actual textbook and put the official theorem, you don't have to memorize that verbatim. You just really need to know this formula here that we've boxed in. But I'm going to put something a little bit more formal in our notes. Which is this here, position from velocity. And then again, this is using the fundamental theorem method. It's just a little bit more of a formal statement. Kind of just putting it all together, really. All right. Does anyone have any questions at this point? All right, so let's actually put this into practice here with this example. We're going to graph the function, determine when the object is moving in the positive and negative direction. We did that earlier. We want to determine the position using the antiderivative method and the FTC fundamental theorem of calculus method. Okay, so just to kind of save some time here, this graph will look like this. We have a 0 at 4 and negative 4, and it's a quadratic opening down. So it's something to that effect. Okay. That's our velocity function, and again, positive motion, velocity is positive from 0 to 4. T is in there. Are we including this 0 here and where the velocity is positive?
Yes.
Are we including the 4? No. All right. Because it's 0 at 4, not positive at 4. And negative when T is in between 4 and 5. Again, not including 4, we will include 5. Okay, so let's see, our function is 32 minus 2t squared. So to determine the position function using the antiderivative method, and if it specifies a method on the exam, you want to make sure you're using that method. If it doesn't specify, use either one you want. So the antiderivative method, we're going to take the antiderivative of our velocity. Is that it? Antiderivative of velocity with respect to time gives us what?
32t.
32t minus 2/3 t cubed. Get it?
Let's see.
Plus c, right? We're just computing in a straight antiderivative, so we need to be mindful of this constant of integration. So when we take the antiderivative of velocity, like we said, that gives us our position function. However, the position function is incomplete because we have c in there. We want the actual value of that c. So again, to solve for c, we have to use the initial condition or the initial position. Initial position, s of 0 equals -3. Here the constant's going to be -3 because we're just dealing with a polynomial. Everything zeroes out. If you're dealing with like trig functions or logarithms or exponentials, not all things zero out just because you put a 0 in, right? So just s of 0 equals -3 to find c. Okay. So we've got s of 0 is 32 times 0 minus 2/3 times 0 cubed plus c, and we know all of that equates to -3. So we have, I'll just write this out, 32 times 0, 2/3 0 cubed plus c is equal to -3 because that is s of 0. So c equals -3. Therefore, the position function is what we had earlier, 32t minus 2/3 t cubed plus c, which was -3. Questions on that? So we have 1 minute. I just want to mention that this position from velocity thing that we saw, let's look at it like this. It's going to be s of t equals to the integral, well, let's keep it in order. They had the initial first, I believe. So they had s of 0 plus the integral from 0 to t v of x dx. But the things that match up here are this t, whatever that is, that t right there is this upper value here. And this s of 0 thing matches up with the lower limit of integration. So it doesn't always have to be 0 and t. We just want to make sure that those things are the same. Okay. Usually it is this way, but sometimes you might have some weird scientist that wants to start at 1 instead of at 0, or whatever. It's all fine if we look at it like that. So we'll pick back up here on Thursday. Let me know if you have any issues with MML and any other questions. I'll see you all Thursday.